Welcome to lecture. I'm always 19 or 20. Doesn't make sense between 1 and 2. 19. Okay. Just scold me. I'm organizing in weeks. That's why. Anyway. Okay. So on Tuesday, and we talked about the renormalization group flow. And the key lesson that we learned is that the eigenvalues of linearizing around the fixed points tell us which ones are relevant variables and which ones are irrelevant variables. And obviously we care about the relevant variables. And just as naming suggests, and the relevant variables are those where the eigenvalues are positive. So they drive us away from the fixed point. And that tells us that these are the variables that have to be adjusted to be at criticality, which is what the fixed point what the fixed point is. And now for today, I want to show you how we can actually learn more from these eigenvalues, namely the behavior as we approach criticality, and thus really can extract the critical exponents. And to that, we start by looking at how does the free energy change under the RG transformation. So typically this, what we learned today goes into as scaling. So remember, under the RG transformation, we go from a coupling K to a coupling K prime, where K is now a vector comprising all parameters, or system parameters. And similarly, the number, what we do is we do coarse graining or blocking. So the number of lattice sides goes from n to n prime, which is defined by nb to the minus d, b being the blocking factor, and d being the dimension of the system. And with the appropriate choice of the transformation of the coupling constants, the partition function stays of the same functional form. So Zn prime of k prime is equal to Z of n of k. So with that in mind, let's look at the reduced free energy per spin. So that's I define as f, small f bar, which is small f over kBt. Remembering f, small f is the nomenclature for the free energy normalized per lattice sides, and here now also normalized by kBt. With this in mind, I can write my small f bar as taking the limit n to infinity of 1 over n ln of my partition function. Similarly, I can define the reduced free energy per spin of the transformed state, f of k prime, which is then minus taking the limit n prime to infinity, 1 over n prime ln z of k prime. And now making use of the definitions above, we can write this as minus limit taking the limit of n to infinity, given that n prime we know is 1 over n b minus d, and knowing that the partition function stays invariant, of the non-prime state. And so from that, if we now compare this to that, we see that the only difference is the scaling factor 1b to the power of d, in which the non-transformed free energy per spin and the transformed energy per spin differ. So we can write the transformed state as b to the d of limit is equal to b to the d of f of k. And so what we did here is now, by just merely applying the renormalization group transformation, we extracted a scaling transformation that applies to the free energy. And that's basically what we're going to do for the rest of the day. We're going to aim to extract how do observables scale under these transformations. And in the slide, we go back to what we developed on Tuesday to now express our system parameters, our coupling systems K, in terms of the eigenvectors around the fixed points of the systems and the expansion in these coordinates, namely again, expressing K as the sum, expanding in the coordinates of these eigenvectors around the fixed point. And thus I can write also my reduced free energy per spin in terms of these coefficients of the parameters. And so that means that my free energy can be written as sorry, the bar missing. So my free energy can be written as b to the minus d of the transformed state, where now the transformed state I can expand as, remember, transforming these the system parameters, now having them expanded in the eigenspace of the eigenvectors was equal to applying the eigenvalue on the multiplying with the eigenvalue of the respective eigenvectors. So we can write this now as b to the minus d transformed state, which is then given by lambda 1, u1, lambda 2, u2, lambda 3, u3, and so on. Remember, so these are the transformed states. Okay. Now, we learned more about these relevant and irrelevant variables. Particularly, we learned that for most ferromagnetic magnetic systems, we have two relevant variables that typically correspond to the temperature and the applied field, and all other variables are irrelevant. So we have, for example, U1 being the reduced temperature, and U2 being the applied field. And all other variables are stable. since we most of the time for now cared about the magnetic system, I will aim to improve nomenclature by referring to U1 as T and U2 as H. That makes it easier to distinguish which direction or variable we're looking at. But this is not a loss of generality of this being true for any RG transformation, since we didn't specialize it. It's just basically renaming here. That also improves readability, obviously. So now expressing it this way, I can rewrite the above equation as a function of T, H, and other variables that I don't care about, beta minus D. And now I call this lambda T times T, lambda H times H, and variables I don't care about. Now, I want to make a claim. And the claim is that I actually know the scaling of the eigenvalues as a function of B. So B is my blocking factor. And the claim now is that the lambda k's scale as B to an exponent A of k, where now this exponent A of k is independent of B. We will reason that this is a good choice, where AK is an exponent of k. Demonstration for that is the eigenvalues are obviously a function of B, right? Because that's this change of scale, that's that one parameter that I'm changing when I'm doing the transformation. So B is the parameter driving my renormalization group transformation, and then obviously the eigenvalues that are actually holding the dynamics of this transformation need to depend on B. So that's clear. The question is how they functionally depend on it. So eigenvalues are functions of B, which is the scale change of this system under RG. So generally speaking, I can write my lambda k as a function of B. Now, say we now perform two successive RG transformations with different scales, B1 and B2. So B1 and B2. Then what would be the total change of scale? So think about the 1D system. It obviously applies for higher dimensions too. So if I first block by a factor of 2, and then I block by a factor of 3, then the final blocking that I have after those two successive blockings is 2 times 3, 6. Then the total change in scale after both transformations is B1 times B2. Okay? And so now, if I express this in terms of the RG transformation, it also needs to be true that my lambda k as a function of B, and then successively applying the next transformation as a function of B1 and B2 also needs to be the same as if I would have done a transformation with B1 times B2. Now, looking at this equation, we see that this is solved by B1 to the power of AK times B2 to the power of AK. That's equivalent to B1 times B2 to the power of AK. Where here now AK is independent of B. And what we're going to learn is that these AK denote the critical exponents of the transformation. So this is the key claim that is we can motivate from how we perform the renormalization group transformation. And in the end, what you need to, and we're going to see an example eventually today or latest on Tuesday. If we have a specific problem, what we need to do in the end is only to identify this scaling of the relevant variables, and everything else is written in stone after that. And what is written in stone, we're going to derive today. So these AK then before are the critical exponents of the transformations in the two relevant parameters, and from that follows the whole zoo of critical exponents that we defined for the susceptibility and specific heat and so on. So we can derive them just based on this scaling assumption, and that's what we're going to do now. Yeah.
So I was wondering why we know that one direction will be the physical temperature, or I guess the reduced temperature, and one the external field, if we have like applied a very, say, general basis transformation beforehand to actually switch to the eigenbasis. So I mean, before we had like the parameters, say, beta times J and beta times H.
Yeah, so that's what I said. Like, this is like, it will turn out, if you sit down and solve magnetic systems, it's going to be T, reduced temperature, and H. But for the moment, this is very general, and this is just like renaming. Like, I'm just choosing for the readability of the next, I don't know, 4 pages that I'm going to write down. I'm going to name U1T, and I'm going to name U2H. That's the only thing that you need to take. And everything else is just that, okay, eventually when we solve it, we see that this is indeed true. But for now, it's just a nomenclature, so that we don't get lost in indices. Just take it as that. So if we now assume this scaling and go back to our example, we can write the eigenvalue lambda t as b to the d, d being the dimensions of the systems, and ct, the critical exponent of the temperature variable, and similarly lambda h, ch, and lambda 3, and so on, b to the d, c3. And with that, our free energy becomes the just writing it down, C3, U3, and so on. So where we use that lambda k, I write as b to the d to the power of ck, which is b to the d ck. So that's saying that our AKs here are the CK. Oh, sorry, CK. And reorganizing that also tells us that the CK are ln lambda k over d dimension, not derivative, ln b. And so we can learn about the critical exponents from the eigenvalues or the signs of the eigenvalues of the variables. So remember, we have now CK is bigger than 0 if lambda k is bigger than 0. So that's for the relevant variables, which drives us away from the fixed point. And we have CK smaller than 0 if the eigenvalue is smaller than 1, and these are the irrelevant variables that are spanning the basin of attraction. And so now I want to make use of this to extract the scaling of the dynamics. And so what I want to do, I want to derive the critical exponents of the susceptibility and so on, the magnetization. And we know that we can derive them by taking derivatives of the free energy. But the way I've written right now the free energy is that I still have the functional dependence within all parameters, and I need to take derivatives. Now, I'm not interested in the specific exact form. I'm only interested in the scaling relationship. And so since I'm interested in the scale, what I'm going to do is I'm going to look at these functional forms and derive so-called scaling functions, scaling forms for the free energy. And to that end, I want to at first make our free energy independent of the reduced temperature by making the following choice. So in principle, I can choose my blocking function B. Okay, done. I can choose my blocking value B as that's just an arbitrary number that I choose. And so since B to the BD is an arbitrary number, I can specify as the choice for that number. And to derive the scaling relationship, I will make the choice that B to the power of D is equal to the reduced temperature 1 to the minus CT. It's just a number. And so if I do that, then this function looks much easier, namely, now the B to the T, this becomes the T to the power of minus D 1 over CT. And now, as a functional dependence, the trick is that this prefactor now cancels, so the free energy is independent of the temperature itself, the function itself. It's only pops up in the scaling up front. And the dependence on H differs now. That's CH over CT, H. And here we have C3 over CT U3, and so on. Now, for the irrelevant variables, we see that C3 over CT is smaller than 1. which yields to that T minus C3 over CT will actually decay to 0 as we approach criticality, which is sending the reduced temperature to 0. As T goes to 0. So these irrelevant variables, we don't have to worry about them when we now, which is why they're called irrelevant. So all irrelevant variables go to 0 in the critical region. And so I can now read off the scaling form 1 at criticality. There's going to be another one. In the limit of sending the temperature to 0, which removes all the irrelevant variables, and that has now the functional form. Sorry, and the C3 go. No. T to the power of 1 over CT, and that's a function now only as a function of H divided by T to CH over CT only. And from that, taking the scaling relation, we can now calculate our thermodynamic variables. So this 0 field specific heat is defined as T to the power of minus alpha. That's the definition of the critical exponent. And now we can derive it because CH, we don't care about prefactors, we only care about scaling, is proportional to the second order derivative with respect to temperature as approaching critical point. And so that's then taking the second order derivative of the scaling function. In principle, like just to motivate, like if I were to just put in the entire free energy without the scaling function, this would be the form b to the minus d bar. Oh, sorry. And from the derivative with respect to t, I would get twice these factors, so b d ct twice. And now again, using this ansatz of the scaling form, at criticality. So at criticality, we send t to 0, having chosen b of d as t minus 1 over ct. And we send the field to 0 to then have ch, just plugging it back in, is t -2 from the second factor and +1 over CT from the first factor, and the scaling form H. And now comparing the definition of this here, the definition and the scaling, we can read off the critical exponent. And so this is as advertised. We find the critical exponent as a function of the scaling of the relevant variables, CT. And this will be, we'll basically continue doing this for the plethora of critical exponent, so that you see how we can derive all of them, but most crucially also remember that I believe in first week or second week, we derived based on thermodynamics an inequality relationship for the critical exponents, and were surprised to see that if you actually perform experiments or numerical simulations, you see that these relationships for the critical exponents holds as an equality. And so now renormalization group will explain that this holds as an equality based on these relationships of how the critical exponents depend on the critical exponents of the individual relevant variables. So that's the first one. And similarly, the zero field magnetization is defined as m minus t, to the power of beta. This definition again. And so in thermodynamics, this means m is minus df dh. And then again, using scaling from 1, we have m is minus ddh of t minus ct phi ch over ct. And that's then minus, just copying the first factor. And then from the derivative, we get a 1 over t ch over ct. And putting those together, we get minus t to the power of 1 over ct minus ch over ct. And so again, by comparison, we read off critical exponent. Let's keep it for later. Still have a few more to go. And with the same scaling form, we also get the zero field isothermal susceptibility. Find as scaling t to the power of minus gamma, and thermodynamic y is defined as the derivative of the magnetization with respect to the field, which is again taking another derivative of the above. And that then gives us a minus t over ct. And there's a factor of 2 popping up from the second order derivative. Which allows us to write this as t minus 2 ch over ct. Ct times the scalar function. And there are different scaling forms. So we'll arrive at the last critical exponent that we need for the inequalities. We here now use that both t and h are both critical. So I adjust them at the same time. And that can be done by scaling form 2, where we chose e to the minus d to be equal to h to the minus 1 over c over h. Write this in. More consistent. And then this we give a different function, a form, but it's the same logic as before. The b to the minus d gets replaced by h1 over 1 over ch. That's obviously a different function, and now depends on h over t ch over ct. And we use this scaling form 2 now to determine the critical isotherm. Which is defined by magnetization to the power of delta, which we can also write following form. And we already calculated the magnetization just above here. Copy this down. Now we use the scaling above to replace t as the variable that I'm adjusting with the field. And then I get now h to the power of c over h minus 1 because of the 1 over ch cancelling. Psi 1. And last, read of critical exponent 1 over delta is equal to 1 over CH minus 1. Okay. So it might read off a little laborious to go through it, but you would imagine you would have been the PhD student to do this calculation, right? You know, there's this ocean of like evidence that this equality is true, and all of a sudden you sit down and you start with this whole, you know, plethora of math and principle that people used to do at the same time of doing this awful series expansion, enumeration, and all that. That's the state of the art, right? Like what a whole amount of work, right? And you sit down and you go through this logic by extracting the scaling, looking at what are the parameters that actually measure, that are actually relevant, and looking at the dynamics, and you find like these, sorry, but you know, mathematically speaking, trivial relationships, right? And then you sit down and you ask yourself, actually, do they obey these equalities? And to that end, we quickly reorganize this as CH over 1 minus CH. Because if we now are taking all these exponents for ferromagnetism together, we find that if we now take alpha plus 2 beta, plus gamma, and we just copy down how we found them. So alpha was 2 minus 1 over CT plus 2, 1 over CT, that's now beta, minus CH over CT plus gamma is 2 CH over CT minus 1 over CT. So I'm just writing this down. Okay, and now I go through it and I see that these cancel with those. There's plus and 2 minuses. And then the minus C8, this one cancels with this one. And what's left is as simple as a 2. And we found that what thermodynamically we would only derive as an inequality actually does hold as an equality as observed and now finally predicted from renormalization group. And similarly, the other relationship was delta minus 1 times beta. Also, if you check for that, that's why I wrote CH minus 1 plus CH over 1 minus CH, popping down the delta down there and multiplying it by beta, which is 1 minus CH over CT. See that these two cancel, and I arrive at this being equal to 2 CH over CT minus 1 over CT. And I can identify this as gamma. It all perfectly falls in place. And also note that we do find the same exponent independent of from which direction we approach the critical behavior. So independent of the sign of the reduced temperature in this case. Also, as F independent. And so, and sign. Yes, there was a question.
Yeah, I'm wondering the magnetization, shouldn't it be 0 if I approach from like for M the
Yeah, that was
behavior
taken.
was different.
Yeah, but that's why we used here the different scaling fold where we adjust both the reduced temperature and the field, because I only arrive as at the magnetization if I take the temperature to 0, add an applied field, and only then reduce the field.
I thought like when we derived the beta critical exponent, we already set H to 0, and then we just let the temperature go to the critical or like small t to 0, so that we get this like second order phase transition. But then shouldn't the behavior only be like square root if I approach from the left of like from negative small t, and if I approach from the right, it should always stay 0 until we get to criticality.
Okay, so this is the 0 field. Okay, so the beta, sorry, the beta is the 0 field magnetization. Okay, and now we look at the where is it here? The critical isotherm, which has this functional dependence, and we only find when we. And now you were arguing about the sign of the reduced temperature. Yeah, no, just before I only mean the beta, not the delta. I really only mean the beta, because here we conclude then that also in this case, there's no difference between approaching from the left and from the right on the critical temperature, because we also have this modulus of T. But as we have in the definition already, okay, we have a minus T to the beta, because only when we approach from the left, we actually get this beta. From the right, we always get a 0. So I was wondering how this is like, can we reconcile? I agree that this is the definition, and I would actually really need to look up the definitions and how this makes sense. For this to be consistent for any general choice of beta, CT, and CH, right? It's so there's the minus sign is there, but it's on outside the zero field magnetization. I reduce the temperature and to 0, and I find but the field is 0. Sorry, I have a hard time to, again, can you argue why I have a minus T there? Or is this the assumption that we took down? You mean for the definition, right? Yeah, for the definition. Because like if you imagine the diagram, there was like, if I approach from the right, the magnetization stays always 0 if the applied field is 0. And then we get the square root, the double. Exactly, bracket. Yeah. And so I only expect when approaching from the left to get the square root exponent, while from the right, I will always be blind and always see that nothing happens. So the behavior is actually asymmetric. So I was wondering how, like, our conclusion is that it's symmetric, but that's at least what in only this case it couldn't be symmetric, it could be asymmetric. And I suspect that it's dealt with the minus sign here, that we're defining the direction of the magnetization, because the magnetization would be 0 from the other side, like if we approach from higher temperatures. That's my assumption, but I need to look it up. Well, there's one other thing for the psi, the other scaling form. Yes. Why is our argument the same? Like not the argument, but like what's in the brackets, the argument. Why is it the same as for the other one? Because shouldn't be like the other way around. If I replace H, like the scaling B to the power of minus D with H equals 1 CH, then I get the 1 in the second argument, and this I delete, and then it just. Okay, so what I'm doing here is that I'm adjusting both parameters. So I'm still holding also that B to the minus D is equal to the previous scaling assumption.
Oh,
So both have to be true. It's like you know, adjusting both at the same time to reach criticality. And that's how.
Oh, okay. Thanks.
So in summary, that's a short summary. There we go. In summary, we have that the calculation of the eigenvalues of our matrix A, which is the linearization around the fixed point of our RG transformation, will give us all the critical exponents corresponding to that fixed point. A. And the critical exponents are the same for all systems in the same universality class, which is now defined by the critical surface containing a fixed point. So it's in the end, what we gain by learning about the renormalization group flow is that we have a way to classify our different systems, because what the variables are doesn't matter. What really matters is how is the flow within this parameter space, and so in the end, it's like maybe I'm now drawing an analogy. Like if you have nonlinear systems, right? You do the same of like if you heard of it, like if you have a limit cycle and you're always going in circles in your dynamics, or if you're approaching a stable fixed point, like the dynamics are the same, and they are only a function of really what does the surface look like, what is what's it called, basin of attraction, which is my critical surface, and what are the directions in which I need to adjust, and how many do I have to adjust. And this alone classifies the critical behavior and not really the physics that goes into that. So as long as we can, and now we actually understand how universality can come up if I can, in this framework now, map different systems onto each other. And that's the key insight that we learn from this new perspective of looking at the flow under renormalization group transformations. And so up to now, this was like after having looked at the example of the one-dimensional Ising model, this was a very formal derivation of the universal properties of any renormalization group transformation. And as I said, as in the end, what it now boils down, the only thing that you need to do for your desired system under study is to find to define the renormalization group transformation, find the eigenvalues, and extract the scaling of your relevant variables. And to see that in action, there's one application, which is the Gaussian model that I want to show you. But to appreciate the solutions of the Gaussian model and how it works through renormalization group transformation, this is a simple enough model that we can actually also have a direct solution. So I will give you the direct solution first, and then see if I manage to give you no, like unlikely. And I will give you the renormalization group solution on Tuesday. Okay, so the interlude is, I'm going to look at the Gaussian model. First of all, with the direct solution. And this is the example from CADA chapter 4.6, sorry. So what does Gaussian model mean? Gaussian model is the Landau-Ginzburg Hamiltonian up to fourth order in expansion. So up to quadratic term in and that means that our partition function is again the function integral over all magnetization fields, with the effective Hamiltonian being the integration over t to the 2m squared. Here we got the derivative term plus, and now we have the quadratic term. And in principle, there could be higher order terms, and we have an applied field. To solve for the for critical exponents, the usual trick is to go to the free energy and then calculate the thermodynamic variables directly. To achieve that, we go to Fourier space. So we define the magnetization field as the Fourier transformation of the spatial field, which means that I can write my spatial fields as sum over e to the RQ x over the volume normalization. So applying this transformation to the partition function, I will only exemplify on the first term. So that means keep the special integral, and I now replace the magnetizations with the Fourier expansion. That gives me two sums over Q and Q prime. E to the minus I Q plus Q prime x normalization squared. And this integral the spatial integral now, integral vanishes unless Q is equal minus Q prime. And that solves the integral, and we arrive at one. We're left with one sum, and the result of the integral is actually the entire volume of the system, right? For delta Q minus Q, for the Q minus Q prime. So that gives then left with one sum, M Q prime over the volume. And similarly, we can transform the higher terms where for the derivatives then give rise to factors of Q to the respective order. So then the full effective Hamiltonian becomes beta H sum over Q. And okay, so the first was a T. There's a factor of 2 everywhere. So there's a T, then the second term gives a K. From the derivatives, we get a Q, that's squared, so it's a Q squared. And then this next term is an L, it's second order derivative, so Q squared squared, Q to the 4, and other terms. And the applied field is, so here, sorry, here the magnetization is linear, right? So performing this integral is only non-zero if the wave factor is equal to 0, right? That's the corresponding wave factor. So we get a minus H M now here for Q equals 0. This is due to volume integral. Okay, so having that, and the partition function reads where the sum over Q became a product over Q. Yeah. Because I've moved it out of the exponential. Sorry, and I'm writing down here. Yeah. So now we want to solve this integral by integrating out all the modes. And to prepare for that, let's first solve the contribution for Q equals 0, which is where the applied field acts. So integration for Q equals 0, which I denote Z0, is then we only have one Q, so the product goes away, and I'm going from minus infinity to infinity. Q equals 0. That immensely simplifies the Hamiltonian because then I only have two T M Q equals 0 left here over 2V, and the Q squared and the Q to the power 4 terms obviously vanish, and H M Q equals 0, which is Gaussian integral we can solve to find 2 pi over t to the power of n over 2 e to the power of vh squared 2t. And similarly, also the non-q equals 0 terms I can map onto a Gaussian integral, just that the normalization factor looks more complicated. So now add the integration for q10 arrive at is vh squared over 2t, and the other terms of the, so that's the z naught term, and now the product of the other terms, they get the normalization of 2 pi t plus q k plus lq n over 2. And with that in mind, we can now proceed and find the free energy, which is then as a function of t in applied field H minus ln z over the volume integral over minus, and then the exponent up front gives an h over 2t. Where we omitting constant contributions. Okay, so what we're taking here is we're summing over all, we're integrating out over all wave vectors q, which means that we're here summing over the Brillouin, sorry, spelled Brillouin zone of the system, and the question is which of these terms are dominating, which parts of this integral are dominating most the free energy here. As we approach criticality, t goes to 0. So, but the strongest contribution is really as q goes to 0, we get singularities here, right? Because the logarithm goes to minus infinity. So these the contributions around small q are the ones that are dominating our free energy. And so having that in mind, we can simplify now the integration over the Brillouin zone, which in principle the integral over the Brillouin, if you did it once wrong, Brillouin zone is in principle, it's like in 2D we would be going from minus pi of a to pi of a minus pi of a in d dimensions. Think about this in the d-dimensional cube. And so a simplification that we can now do, because we know what actually contributes most is the point in the middle, the q equals 0, is to simplify the system by a hypersphere, to approximate by a hypersphere. So we don't care, we neglect the contributions in the corners. So we approximate by a hypersphere, hyper being like a sphere in d dimensions, as the contributions close to pi over a are less relevant. So why is this cool? Because then all of a sudden I can really write down my d-dimensional integral nicely as a spherical due to spherical symmetry. So the spherical symmetry simply integrand. And so then the free energy, particularly as approaching the around the singularity, I can write as n/2. This is the d-dimensional solid angle factor. And now we integrate Q from 0 to, sorry, I should have noted this. This is what I call lambda. And lambda goes from now 0 to pi over a. That's our hypersphere. dq integration constant d to the -1 lambda. And the integrand I'm copying down, q k q to the 4 plus minus h 2t. Now to solve this integral, I rescale my integration constant q with t over k, which means that I define my integration variable as q over k over t. I'm doing this, well, that's basically the same as we did for the scaling functions, because with this choice now, the contributions here linearly, the q squared here simplifies, and I extract and copying down the prefactors. Okay, and now from the rescaling, I get a contribution of t over k to the power of d half. And now I go to lambda k over t dx x d -1. And then I have an ln t plus an ln 1 plus x squared plus l t x to the 4 k to the 4 minus h 2t. Yeah. And now I can see that these contributions here are higher order, that I have no, well, I ignore the, I ignore the higher order of the contributions in the reduced temperature T, and subsum this as a constant for behavior around the singularity. So we here now ignore the higher order dynamics, which means that the behavior is actually governed by the impact of the field, and to leading order the singular, oops, behavior is, and now that's again the choice of this scaling. We get the t t to the power of d minus. That's subsumming the first term as a constant, plus, and the second term, the applied field, then gives, due to the integration, over 2t1 plus d a half, which is I assume should scale by definition of the critical exponents as t to the 2 minus alpha. And so from that, I can read off my critical exponent alpha as 2 minus d over 2 for h equals 0 and t equals 0. And I can, for example, calculate the susceptibility, as the second order derivative of the free energy with respect to the applied field. And that then gives me this contribution only, the d minus 2 cancel, and so that's 1 over t. And that's defined as t to minus gamma, so I read off, for this case, that gamma is equal to 1. Okay. So the aim of this exercise was to now to derive explicitly the critical exponents for this Gaussian model, and now show that we can arrive at the same result with the renormalization group transformation. So, and then obviously the renormalization group transformation we can also use in settings where a direct solution is not possible. So now we look at the renormalization group of the Gaussian model. And so the idea here is now, I go back to this, what we actually do is, we go in Fourier space, we have our Brillouin zone, and what we did in, to solve now for the singular behavior, which is dominating the dynamics at q equals 0, is to go to the hypergraph of radius capital lambda. And now my renormalization group procedure is to whole grain and rescale in my Brillouin zone, so that I define a lambda prime that is now lambda over b by blocking. So my RG here is to go from lambda to lambda over b. Note, by doing that, I coarse grain out the the large Q contributions, which are irrelevant for the critical behavior, which we know dominates at the singularity. So as I said, the idea is to perform RG on the Fourier modes. Use this approximated zone. With the hypersphere. Remember the partition function as set up in the Fourier setup was then minus, nope. Q to the 4. Q 0. And so now to apply the recipe of the renormalization group, what we do is we coarse grain or block procedure, which means that we eliminate fluctuations at the scale from AX to B, which means that in Fourier space, we remove the Fourier modes with wave numbers lambda over BQ, those out of those. And those modes don't hold the singularity. Which is at Q equals 0. So this coarse graining now, what does it do to our partition function? Well, it means that we can now, we have two factors of the partition function, one going from those modes that we're taking out, lambda to B over B to lambda, and the remaining part of it. So our partition function then becomes, and I'm dropping the functional integral for the moment. The functional integral I keep for the terms that I'm still integrating over. So exponent V, now those that we coarse grain out. And that's the integration at the rim of the layer zone, which now I abbreviate as e to the minus v f delta f v boundary, and the remaining modes. Which now go from, minus 0 to lambda over b, and that's just copying down above. So that's the first step. Now I want to we need to find the renormalization transformation, and so to that end we need to find out how we need to rescale our variables such that the partition function, the functional form, the partition function stays the same. So rescale by setting first the space dimension x as x over b, which translates to momentum space as q as bq. And under that, our partition function, now you know why I had this abbreviation, so I don't have to copy that down, at delta FBT dq so rescaling our q's with this b means that I get the minus bd t plus qk squared b minus 2 yeah, plus l b minus 4q times plus h. This is all now h m. Yeah. And last, I renormalize to now find our transformation. And so we renormalize the magnetization m prime of x prime as m of x prime over xi. And in Fourier modes, this translates to m prime of q prime equal m of q prime over z. And note that z is not xi, different space. But with that, I can now write my integration over the q primes as, okay, almost there, d2q so from the magnetization squared here, oh sorry, squared missing, oops, I get the z over 2, and the rest I copy down. Okay, so now we succeeded in writing down the partition function in terms of all transformed variables, the magnetization, and the Fourier space. And now we want to read off the transformation by comparing this partition function with our original partition function, which sadly is over here. And it should be of the same function form. So that means that we can here actually read off, first of all, the renormalized parameters. We can read off. That means that in this case, my t prime is this whole thing. So it's b to the minus d z squared t. My h prime is z times h. My k prime is z squared b minus d minus 2k. And my L prime is z squared b minus d minus 4L. Okay, so that's the transformation rule that I can now we can now read off. And so the what needs to be true under this transformation is that the singular point is mapped onto itself. And that's true because the singular point is t and h equals 0, and they transform onto each other. The fluctuation scale, so the parameters should remain invariant under the transformations. So scale should be invariant. If stays fixed. And so a choice to do that, if we look at the K, is to state that I choose Z as b to the power of 1 minus d half. Because what does it mean? It means that my K prime with this choice 1 minus d half to the power of 2 times b minus d minus 2k maps onto each itself, right? But what happens to our second parameter? This one, sorry, there's a plus. To the power of 4, b minus to the power of 2, sorry, to the power of 2. But here this is a power of 4. L, this scales as b minus 2L, which means that under successive transformation, it goes to 0. So it's the irrelevant. It's not contributing to the behavior at the singularity. So we see that the two relevant directions are t prime, which is b minus d, b1 minus, sorry, to the power of 2, t, which is equal to b squared t, and h prime, which is z times h, so b1 plus d half times h. And there we go. This is exactly what we needed. This is telling us the critical exponents of our relevant variables. And so we can directly now read off that here CT is equal to, and here CH is 1 plus D halves. And then, for example, using the relationship that we derived in a very general case for alpha as 2 minus D over CT, we here get 2 minus D half, which is in agreement with the direct solution. So this hopefully exemplifies how the renormalization group approach allows us to directly find the critical exponents of the relevant variables, and thereby leads us to identify the entire plethora of critical behavior at the specific fixed points. And that's the end of our journey to the renormalization group approach. And I'd like to thank you for your attention.